Alright, hello everyone. My name is Gantt Meredith, and this is my exam 3 topic, optics. Let's go ahead and get started. So before we begin, optics was personally one of my favorite areas of study from physics in high school and physics in college. It's very interesting, and there are many aspects to optics that we can study, but for the purposes of this class, we'll be focusing on the opacity of compounds, and we'll get into what that means in a minute, or the opacity of materials, excuse me. But before we do that, it's important to lay some groundwork, some foundation, so that we understand the concepts that we're studying. So first of all, what is optics? Well, it's the study of light. And specifically in this course, we'll be focusing on light passing through materials. And then that can, as we observe the amount of light that goes through material, that will lend some information to the properties of the material, and we will again touch on that in just a moment. So one of the most important items to consider when it comes to optics is one of my favorite law, honestly, is Snell's law. Now, Snell's law has to do with the light that is entering a material, and then based on, it's called the index of refraction. The index of refraction, N1 over here, if we assume that we are in air, is going to be 1, and then the index of refraction inside a material will be different than air. Normally, the index of refraction is going to be higher, and if the index of refraction is higher, then the light rays will be refracted more, and that yields this rainbow structure that we get down here, and I'll explain that in just a second. So when it comes to Snell law, we have to consider three things. We have the angle of the light that is incoming, theta 1, the angle from the normal that light then creates once it has entered the material, theta 2. We have the indices of refraction of the outside substance and then inside the material. And then we have v1 and v2, which are the velocities of the light at each different position, so outside and inside the material. Now, why do we get this rainbow structure down here? How does that happen? Well, that's because white light, right here, light that comes into a material, consists of all of the visible light that our eyes can see. So we can think of Roy G. Biv for all the visible light that our eyes can see. And the reason that light gets this rainbow structure is because once the index of refraction is higher inside the material, that means that there's going to be more hindrance inside the material, and this hindrance is going to cause each wavelength of light to slow down. So the velocity is going to decrease, because as we see, as the index of refraction goes up, velocity will decrease. So that means that with more hindrance, the light will slow down. And we know that speed has to do directly with frequency and wavelength. And so visible light is present to us in different wavelengths. That's what our eyes can see. There are multiple wavelengths of the electromagnetic spectrum. We have radio waves, microwaves, infrared radiation, visible light, ultraviolet, and then X-rays and gamma rays. So we're focusing on visible light for optics in this course. And all of these different colors have a different wavelength of light at which they're visible. So once light begins to slow down as it enters the higher index of refraction, these different wavelengths will become visible when the light is refracted out of the prism, in this case, and out towards our eyes. So for this course, we focus more specifically on the intensity of light at an interface with the solid. And when we look at light interactions, we can determine the total intensity of light by adding up the 5 different intensities that this course focuses on. The first intensity is the intensity of reflected light. So when we have incident light coming in here, it is then reflected, some of it is reflected off of the material. That's the reflected light. The incident light is light that is coming into contact with the material. The material is this gray rectangle right here. Now the third type of light that we have is the absorbed light. And, excuse me, the absorbed light is just what it sounds like, the light that is absorbed into the material, the light that is not moving fast enough to leave the material, and it bounces around and refracts inside but never leaves. Now we have the transmitted light, and this is light that transmits directly through the material, so it's pretty self-explanatory. Then we have scattered light. So scattered light is similar to transmitted light, in that the light rays the electromagnetic spectrum waves make it through the material, but instead of traveling straight through, they are scattered based on the properties of the material. So say if we had a material with a very high index of refraction, the rays would scatter, and the scatter rays can even yield a rainbow like we saw on the previous slide. Now, for the purposes of this course, we can classify materials based on how light travels through them and how light interacts with them. So you can see here we have 3 different samples of aluminum oxide. Now, based on the properties of aluminum oxide, we can alter them to make a transparent, a translucent, and an opaque aluminum oxide. Now, the opaque aluminum oxide, as you can see, you can't really see through it. You can't see the text beneath it, and that's because it has a very high index of refraction and it doesn't allow light to pass through. Now, the lowest index of refraction is going to be all the way on the left, the transparent aluminum oxide. As you can see directly through, and you can see the blue text no problem through this material. Now, translucent is somewhere in the middle, so it has an index of refraction in between transparent and opaque materials, and translucent means that you can still see through the light, but quite a decent amount is absorbed, and we cannot see as clearly as we can with a with a transparent aluminum oxide. That concludes everything we need to know for optics that could show up on the exam. Again, a reminder that optics is a very wide topic, but for this course, given the brevity and the amount of chapters in our last module, these are the highlights of optics that we need to focus on and consider when it comes to conceptual questions. Thank you.